Good evening, everybody. Can you hear me?
Yeah, Professor.
Okay, thank you. Today we are going to discuss about the hydroelectrical power generation. We'll see how we can proceed that energy generation by hydropower, as well as I would like to discuss with a little bit about energy storage. Actually, the hydropower is very much oldest renewable energy source in the world. The technology was developed very long time ago compared to the other source of energy, especially the wind, solar, and the one. Then the people found that this technology a long time ago for some other application, not only for not for electrical generation, because of actually these technologies are developed to fulfill the requirement of the society. Then actually the water mill, the windmill, like that type of requirement was there. Then the mill is used for the milling purpose, especially for the flour and the grains, giant different grains. Then people require the mechanical power. Then this is one of the oldest the technology people use to harness the hydropower, which we are calling this a water wheel. The water wheel concept in is the first technology that required not much high head than the water flow, and the water wheel is there. Then this water wheel is rotated due to water has some amount of potential energy due to that the flow from upstream. Then it convert to mechanical energy. That mechanical energy is used for this type of application. Then there are some technologies people are used for the water wheel. Then we are calling the water is going the downside of the wheel is a one technology. Then we are calling the best slot wheel. Then other technologies, the water can be going the upside of the wheel. These two technologies are there. That's depending on the architecture. Generally, this efficiency of this type of wheels are not much high. This around 50% efficiency, less than 50% sometimes. However, it can be worked with the low head as well as the technology also not much required. Then the low RPM, the water also work with the low RPM. Depending on the water quantity, it can generate high torque because of a torque. The torque is a main component people require for the mechanical energy for a grinding ply and other applications. Today I would like to discuss with some technologies, not much at deep level because of this application level. We are not going to discuss that. However, to get some amount of know-how of this technology is the main purpose of this lecture. Now, the concept of hydropower. We know the hydro, the water. Water may be in a higher level. It can be some potential energy. That potential energy can be used to convert. That potential energy can be converted to the useful energy sources such as mechanical power. Then these are the main configuration. Those are main configuration of that hydropower. The reservoir is there. Then as a penstock also there. Then after the penstock, the water going into the turbine. The turbine is the main component we are going to discuss about that. Turbine can absorb that energy and convert it into the mechanical energy. That the mechanical energy can be converted to the electrical energy by using generators. There are the two types of turbines people are using. Turbines mean is to convert hydro, the current, that energy content in the high water convert to the mechanical energy. There's two types of turbines we are using this. The one type is the reaction turbine. I would like to explain a little bit about that. What are the two types of that? Reaction turbines is the one type. Other one is the impulse turbine. It's a reaction turbine. The few type of reaction turbines are there. The Francis turbine, as well as the Kaplan, the propeller turbine, as well as the cross flow turbine. Those are the turbine. There's a configuration of these turbines are different. Then applications also these turbines are different. The Francis wheel and the Kaplan turbine, the propeller and the cross flow. Actually the Francis wheel is the most common use for a high efficiency, the hydropower, large scale hydropower. Then the Kaplan turbine is some development of Francis turbine, because the Kaplan is used for very low head. Then the propeller turbine also using low head with low flow rate. Cross flow also, actually these type of turbines, the cross flow and the Kaplan turbine is using for a low head. The Francis can be used for both the high and low head up to some level. Now, actually energy. This energy is the water. Actually, energy is depend on generally that energy is due to the flow rate as well as head. So those are the main two parameters we can find out. There's amount of energy, head and flow rate. In some site we have head, large, it's a large head we have, but a very low flow rate, high head, low flow rate. Sometimes we have high flow rate and low head. Now, actually, we have the high head, low flow rate also. There's energy. The high head and low flow rate also energy. If you have the high head and high flow, it's good because of there are large amount of energy. Then we need to use different technologies to harness energy from these two type of things. Generally, if you have the high head one, we can use impulse type turbine. Then as well as we not need to handle large flow rate. We not need to handle large flow rate. You can see here, if we need to handle large flow rate, we need large amount of equipments. Because of the flow rate is the issue here. Because of if we need to handle large amount of flow rate, need to be the large size of the penstock, as a turbine size also need to be high. Then this a turbine. The size of the turbines is the large if you have large flow rate. Then if the high head, low flow, that means the turbine size is low. Then even though the very small turbine can be generate the same power, because of the power is head and flow both involved is there. Now, those are one of the main components. Generally, the river flow is coming there. Generally, small of the head required. Head means generally you can see it here. There's a turbine level. There's a water level. The water level up to here we are calling head. It's a total head. However, due to the penstock and other equipments, then obviously there are some head loss should be there. Then we can consider separately those things. However, the theoretical head is depend on the turbine up to the turbine level. What should be the water level at any point. Then, however, then here this type of one as a total up to turbine one. However, there's another point is there. Then there's a total, the energy conversion from here to here. This net head is coming here. But net head, that means the effective head is depend on how much of the upstream side as well as here also. Some side is there. If it is that level is below that point, the net head amount of energy transfer from high elevation to the low elevations. Now, shall we take some concept of this turbine? For a large-scale hydropower, so we are not going to discuss too much about the large-scale hydropower. It's different technologies. The large-scale one, it required not only some multidisciplinary civil engineering, mechanical engineering, electrical engineering, environmental engineering, because of the large-scale one, the complex scenario. For a large-scale one, the technology also, the huge amount of involvement for that one. However, for a small-scale one, when we go for a small-scale one, then the technology is different because of need to be used very not much sophisticated one because of energy. As we discussed earlier, the energy mean the important factor is the cost of energy. Need to be reduced that cost of energy. Now, this is a bunky turbine. We are calling the cross flow turbine. It's very important. The turbine people are using for a small scale power generation. Then actually, when we consider renewable energy, what do you think about the efficiency, conversion efficiency? Actually, conversion efficiency is depend on the resources. If we have that resources are very much expensive, that means that is scarce of that means that means scarcity of that resources. We need to much attention for the efficiency. However, when you go for a small scale, that means small hydro, the pico hydro, then the water, amount of water may be not the issue because of we have the sufficient water because of we are not going to make any reservoir, large amount reservoir. Then the water exists in place rainy days. If there are a large amount of water, we are not going to utilize all water also. Then there's a bunky turbine, the cross flow turbine is commonly used for small scale, the low head type one, because it's much easier to fabricate one. We are going to discuss a little bit what are the configuration of this type of turbines. Now, this is also the reaction type one. Especially the meaning of the reaction type one, there's water. The water fill through all this, the propeller. Then the torque is converted to that the energy conversion, not by the impulse due to the flow rate. There's a flow rate of through that propeller. Now, the configuration of the cross flow turbine generally like that. Here, you can see here. Here, there's nozzle is coming there. So nozzle mean again the water coming from high head with high speed. One, this nozzle is coming there. This is a rotational drum. We are calling the cross flow type because of the meaning of the cross flow. That mean that the axis, the flow is coming in this direction. The rotational axis is the perpendicular that means crosswise, not in line with the flow rate. That's the name is coming there. The configuration is cross. The cross that the water is across the propeller. We are calling this a cross flow. Now we can see here. This configuration is very much simple. The water is coming there. There's a propeller. Then the water has some kinetic energy. Then after it release that kinetic energy, that energy absorbed by this runner. Actually, we are calling runner. This runner part is here. There's some effect is there. It come to the inside, that the middle part of the runner as well. There is some amount of energy in the water can be absorbed other side of the runner also. There's a two type. The pass, two pass is coming there. However, the conversion amount of energy may be different. Shall we think about like that? Because of, shall we think now, these are velocities there. That big velocities there. Shall we think mass flow rate is there. Energy. The kinetic energy we can write here generally. Vp squared. Shall we think this is the V1, V1. Then shall we think some velocities here V2, V2. That is energy input. Energy input. Here it's output energy. We can write like that. Then energy absorbed by this rotor, we can put power. We can say that energy like that. Then there's a conversion efficiency is dependent on. If we make much lower that D2 value, it has much more energy can be absorbed by this type of turbines. It's a kinetic energy concept. However, this type of propeller, it may have, if they have some potential energy, also can be absorbed because the pressure also there. The pressure is some pressure component is coming here, some potential energy coming here. Now there's some other configuration we can see here. The guide vane also here. So why is a guide vane? If we need to control the flow rate, then we can. There's a guide vane is there. We can cross that the flow path. That flow path can be close to control the flow rate here. Then amount of power delivered to that the water power come to the propeller can be controlled by this type of guide vanes. Then actually the controlling part also I would like to discuss with a little bit because of that that is hydroelectricity. Then this propeller is connected to the generator, electrical generator. It need to be run at a certain rotational speed to generate power because of the RPM was very much critical. The reason is that because of the power quality, the control side also some other simple technologies we can use for small scale power generations, especially like that type of power generations because of we know the demand and supply. To supply mean the amount of water and the supply is depend on that is the amount of water is coming from here. However, in the guide vane operations, we need some control in that, feedback control in like that, because of need to be sense the rotational speed with respect to the rotational speed. The guide vane need to be controlled. That means the guide vane need to be manipulated. Then with respect to the rotational speed, we need to keep that rotational speed of the system some constant value. Like that, if our demand is increasing, then what happen? RPM may be dropped. Then at that point, we need to increase the water flow rate to make the builders the required RPM. If it is the demand is low, the similarly RPM become increase. That can be increased. Then it need to be controlled again. However, that complex scenario cannot be used in the small scale hydropower system. Then at that point, the dummy loads are used in there. Then we are going to use the constant load always. The constant load is operating. Then actually the constant load is can be divided by two parts. The real load. The real load is maybe the supply to the demand. Then as well as the dummy load also operating. Dummy load can be varied. Depending on the variation of demand. Then like that type of concept people are using. However, at that point, we are based in some amount of energy, obviously, because of dummy can be dissipated as a heat energy. Like that type of things we can use for a small scale power generation. The reason is that the complex control may be not reliable to operate some places. However, for a large-scale wind turbine, large-scale hydropower is not work like that because of the water is expensive. The water can be saved in the reservoir. Then the water is not going to waste by heat source anyway. Then there's a controlling. There's a proper controlling need to be implemented. This concept of bunky turbine, yeah, called the cross turbine. We are not going to discuss in this level much application side. That means conversion efficiency, what are the blade angles, how we can decide that the flow rate with the nozzles and all those things. We will learn that later. It's a technological concept. That means only concept we are learning here. The application, that means real application level, we will learn later how we can design level, that means application and design level, as well as optimization concept and everything we will learn later. This is a concept of bunky turbine. Okay. Now, yes, this is some better configuration which there is a water path we can see here. Then the vane also there. Then the water flow, the shaft and everything. Those are the controlling concept. Actually, this cross flow is commonly used for a small scale places, very small scale places. Actually, I would like to discuss with you what are the type of generators. Maybe as this level, we should have some know-how what type of generators. We know the two type of machines are there. We are calling that induction and other one coil one. Then actually for a simplification, we can use induction machine for this type of cross flow turbines, because of that is much cheaper. That can be governed by other frequency sources, as well as the double load also can be used for them. Then some places we know that the head also varied. Head may be actually for a small hydro. Then very small dam is that we are not calling the large reservoir. However, very small storage we are generally using here. Then here that reservoir water level is varied. Then we are using more moderate head hydro to take the constant output. Now, shall we go for other slide? When we talk about other type of turbine, we are calling the Francis turbine. The Francis turbine, yeah, the concept of the same, we can do the same configuration. Here, the Francis turbine, as well as the Kaplan turbine, the water is entered from this side, and the rotational axis is other way around. So there is not a cross flow. You can see here. Then you can see here. This is the rotational axis. Axis is here. What is coming there? What is coming there and going down here? This shape of the propeller, is a combination of the Francis wheel configuration I can explain soon. Then this pathway of the water is coming in inside in horizontally, and then going this upstream is going down like that. Those are the most common reaction turbine, the most common reaction turbine. Then there's a tail. Actually, we are called the tail. There's a tail water also. There is a total filled with there. Here is this line is totally filled with water. No any air cavity inside there. That's the main concept of reaction turbine, because of the totally filled with water with the propeller. That's the reason generally the people maybe we can use little bit the tail water level also inside. Actually, this turbine need to be submerged. That in the under the water. We are calling under the water. Then actually that the bunky turbine, the cross flow turbine is not required that concept, because of the cross flow is the semi reaction type one, because of it's not the fully the turbine, the rotor is not under the water, the fully not merged with water. Here that type of the Francis wheel turbine is this type. This is very much fully closed conduit. There's a closed conduit. Then there's a generator. Generally, that generator also in the vertical axis can be connected directly to the generator. Then the most common way that we can use here, the rotational speed of that the turbine need to be comply with generator RPM, because of we know that we require to maintain certain rotational speed of the generator. Then it need to comply that. When we're going to design this type of the turbine, then we need to much concern about the generator, number of poles and everything, because of it need to be the generator constant the frequency which is comply with the utility. Now, the concept of the Francis wheel, you can see the Francis wheel here. That's a wheel type. Generally, water is coming there. Actually, water is the water is around that propeller. Water's path is going like that. Water path is like that. What is coming in this direction is path is like that. It's going down. What is in this direction? Actually, the main configuration is that we are calling rotating part is runner. That's a common name of every turbines. The casing we are calling spiral cases there. Generally, that is spiral case. The water inlet is coming here. It is come here like that type of spiral. The diameter of end of the spiral is small. Here, the inside is large. The reason is that because of some amount of water is passed through the turbine, at the end point is not much of water need to be handled. That's the reason the end point may be at the end of the spiral case becomes smaller and smaller. Then you can see here the size of the capacity and everything. It is very complex geometry. Then in the context of engineering, we need to be consider all this how we can design this all that the size of all this case. Then there's angles and everything, because you can see the angle also. They are the propeller the vanes and angles. There are special angles because of it is shape is water is come into the side in the horizontally, then it release vertically. Then a path is coming there. There's a path is coming there. Then the same way, if we need the kinetic energy concept here, when you go for again that kinetic energy, there's a kinetic energy. Here some energy is there. So energy 1 and energy 2. Here should be approximately, it should be 0. That's the point here, the all energy can be absorbed. Here that velocity should be almost very low level. It not become an absolute 0. They are a very low level. Then that is the point here, energy should be 0. There's a proper turbine that the flow rate, that's the reason it requires large draft tube to handle same water flow, because of the velocity is low here, very low velocity. We know the water is incompressible, and the water we can consider as this water is incompressible flow. However, that speed is that the flow rate is very small, then the size of the tube should be large. Then we can think about how much of the capacity, how much the size of these tubes and everything. Now, generally, there is some the veins are there. So vein, the vein is used to direct that. The vein is used to direct that the water to this propeller. Then this vein angle can be changed here. This vein angle, actually this water guidance can be changed here. Then depend on that velocity and flow rate, the water guidance need to be changed. Then if you need to control this type of turbines, then generally this water guidance is a controlling mechanism. Then this shaft is connected to the generator. Then depending on the power delivery by the generator, however, need to be keep the constant rotational speed that the water guide device need to be operate continuously. Then the concept of this there, how the water flow inside that turbine, then that is coming, water flow is coming there. Then it is, those are the guide vanes. So guide vanes is directed here to that runner blade direction for the maximum conversion efficiency. The guide vanes is coming here. Then ultimately is a middle, there's a middle path. Then that middle path is a water flow. This again coming there. It's a moving blade is there. Then there is water redirected to here. Then through that water line, through that water line is fully filled with water line. It reduces that this energy of the water is absorbed by the runner smoothly, because it's a part of that. This all energy contained in the water is smoothly absorbed by there. Then ultimately, with the shape of that one, because of here that is speed of generally here that is speed of very high. That's the reason its diameter is high. Then it is becoming speed is lower and lower. Then it is diameter is low. Then that's concept. The design concept is coming there. We know that there's R. Rotational speed is omega. Then it is R1. Mean here that speed is omega R1. If it is go for that one R2, that speed is omega R2. Here that we know that omega R2 is higher than omega R1. Then because of that speed reduce of the flow rate, then ultimately with all energies absorbed by one. Then, this is the technology we are using that a Francis scale. It's a somewhat advanced technology. Then this Francis wheel can be used for high head as well as a low head both. Now, again, some configuration like that. Now, this advantage of the Francis wheel is high efficiency at a low watt head. So why? Because of if you go for a site selections, not only for a small hydro, the large hydro, as well as many places. So low head sites are commonly, most of the sites are very low head site. Then we know that a large amount of water is available at a low head places. Then this turbine is very much useful to harness that energy in low water head, especially in Sri Lanka. Also, many places are there. Then some large the large hydro plant also using this type of one. Then actually here we can use for a very optimized performance. Then the control, there is a controllability also exactly very easy. Then can be controlled. That means that RPM can be controlled exactly. Then the Francis wheels are commonly used for many places. The thing is the main point. The main point of this type of the things. There are some disadvantage also. Then it cannot be used for a large high head one. Other one is very complex and expensive, as well as because of the reaction type one. Sometimes the cavitation issues are coming there. Actually, the cavitation issues we can explain a little bit thermodynamically. We know that the pressure. There's a pressure inside this turbine. Shall we think it is coming here? That there's a turbine is going there. Like that. However, that was underwater. Then here, this water is coming there. Here, then with the high speed, the pressure drops. The pressure can be drops. Then it is below the vapor pressure because of water can be vaporized. You can see here, even though the low temperature, water can be vapor because of that vapor pressure that depend on the vapor. When you check your steam table, you can find out that the which type of the pressure at point of some places. Then we are calling these places the cavitation, formation of cavitation. It's a common problem of the Francis turbines. Then here those are the even though there's disadvantages, we can use for many applications. The efficiency of this one is much more high actually. We are calling that the hydraulic efficiency is the high amount of at the low head turbines conversion efficiency is much low. When we discuss about the thrust flow turbine, generally conversion efficiency is somewhat low. It is maybe less than 50 sometimes. However, the complexity wise, this is much high. However, that conversion efficiency is very high. Now, it's another one. It's a coupler turbine. It's a coupler turbine. This is the second development, some development of the Francis turbine. The coupler turbine has not that some component of the Francis turbine because of the vertical component is not much because of here that the energy is not absorbed by this part. It's a guided to that part. Only the propeller, that is propeller type, a large propeller type is used in the other direction. However, it will direct that. The main important one, coupler turbine can be used very low head, very low head. Then the coupler turbine is very much used for very low head turbines. It is the low head turbines, very low head turbines, low head turbines, very low head, very high flow, high flow, a high flow. That is compared to the Francis wheel. Then these are the component type one. Other all configurations and concept is much more similar to the Francis turbines. The only thing is that the propeller, the shape of the propeller, the blade and everything is different. You can see the water is coming there. This what is coming there. Then is guided to the shape of that the propeller body. The water is directed to the downside, then it can be absorbed by this blade. So the large flow can be handled here. Now, this conversion efficiency of these turbines, little bit, we can talk about that little bit conversion efficiency. shall we think here that the water flow rate is coming here. Here is that velocity, the peripheral velocity of the runner, V in. Then angle between that peripheral velocity to the real angle of flow rate, we are calling beta in. As well as a similar way, the beta out, because of there's the outer side of the turbine, there's the inner side of the turbine. Then actually, this is the common configuration of the reaction one. Then there's a radius from a radius in mean to the outer diameter. There's an inner diameter one. Then the torque we can derive the torque from this equation. That means the flow rate is there. The flow rate, the torque can be derived by this equation, rho flow rate, as well as the velocity is coming there. Velocity difference. What are the velocity difference in and out and flow rate? There's a mass flow rate. It's a mass flow rate. We can derive the torque from here. There is a power can be derived by torque into rotational speed. Then that is this equation. This is a common equation. This is a very common general equation. We can derive that the power by we are using this type of Euler turbine. It's a common configuration. However, when we consider Francis Kaplan as well as the Bunky, almost similar to this configuration, it is much more complex. We need to think about this, some other all geometrical angles and everything for this type of calculations. However, now the conversion efficiency, now we can know that because of energy is coming here. Shall we think that energy point, energy here, that energy is this one. Then it's a hydraulic conversion we can write. So power divided by how much of energy is coming here. This is the again that head is coming. There's the total head. This is the potential energy with the head and everything. HROG is converted to how much of energy is coming here. Then this is a conversion efficiency of these type of turbines. Then we can see here, it is very much important factor is this omega. This omega is important factor that is this omega is need to be designed with that geometrical parameters. Then all is interdependent. Turbine rotation speed need to be maintained certain value that is correspondent to the geometry of this all-wheel angle and everything. We can discuss these things in your future classes when we're going to learn in detail of hydropower. Now, actually, when we go for a higher turbines, we are calling that head is very high here. This head is high. Higher turbines, this is the head. We are calling this head. Head is high. Then obviously the penstock length was also very high. Then the dam and some reservoir. That's common for large and small. But the size of the reservoir, that means because a small scale one, even though run of the river one also is small tank we are using to collect that water to feed it to the runner. The thing is that for a large hydro totally that a high, the large amount of the large reservoir people are using, but for a small scale, we are not using small, very large reservoir. This turbine. Now we are going about this turbine is high-end turbines. High-end turbines, it need to be handle high kinetic energy as with the low flow rate. Then there's kinetic energy with low flow rate. Then there's a Peloton wheel is the commonly used one, very oldest concept. The Peloton wheel is the concept of the high head turbine. We are called the impulse turbine. That's the impulse type turbine mean it uses the impulse technology to absorb this energy. So not like reaction one. That means the water jet is using here. So not a vane. For a reaction turbine, is a vane is used there. The vane is used for a direct that wind to propeller blades. But here that we are using nozzle. There's a nozzle is there. The nozzle is used to make impulse on top of that the bucket. The bucket is using here. Then this is a Peloton type one. The Peloton concept is here. This nozzle, the nozzle generally there's inside the nozzle small control plug is there. Then that can be control the flow rate by moving that one. It is the one concept. If you go for a move to that side, there's a nozzle can be controlled the flow rate as well as it is going back. A large flow can be allowed. This jet is there. The jet is there is a bucket. Generally, this bucket is the two buckets we are using. There's a depend. There's a to utilize the all water without wasting. Then this bucket is the jet is coming here. There's impulse. Then water is going out there. Here, it works in the under general environment, not the complete fully under the water. The jet is here, then you can see here, then the velocity difference. It's a velocity difference is convert to energy. Here is the some energy. Generally, however, jet velocity is equal. If there are no any friction, if there are no any friction in this bucket, these velocities are equal. Then that impulse can generate power. You can see here. You can see here the concept is here. The jet velocity is there. Then as the bucket velocity also the same that then you can see we cannot absorb any energy. Then you can see here. Then it's a bucket velocity. It's a bucket velocity within the Peloton hub velocity use U. The V velocity is V. Then is a V and U. The combination of what is V and U is very much. U is the very much critical parameter. V is constant. The V is depend on V is depend on reservoir head of the size of the reservoir. Actually, the head of the head that is dependent on the water head. U can be our design parameters. What should be the U? You can see here the U is equal V. Then no any impulse because of the same direction. No any relative velocity in between that. That relative velocity should be there. If the U is stationary, a large impact is there, but however no energy because of there are no any movement. This movement also should be there. The movement and the force. The energy is the force into movement. The force into movement. That means the F and U is the energy. That means we need to make it the F need to be high as well as U also need to be high. The both cannot be do there because of the U is 0, F is high. The U is large, F is 0. That is going vice versa. The U is lower, then F is high. Then the U is high, then F is become lower like that. Then we are going to check about this, all those things. There are some questions. I can explain this question little bit later on after discussing these things. Now, I would like to explain that so the V is depend on height. Shall we use that Bernoulli's equation type energy conservation one? The V is the 2gh. That is a square root of 2gh. Now, the V is depend on the geometry of the site. This is the conversion, energy conversion efficiency. I would like little bit explain that because of otherwise you cannot understand how we can calculate the conversion efficiency of the pellet and wheel. Then shall we then the bucket is there. Generally, this bucket is that there are some angle is there. There are some small angle here. It not come to this direction, it's some angle, it will the water is go outside of there. What is coming in this direction? What is this? The jet one. It's divided into two parts. Just divided into two parts. Then it's mostly turn there. It is going there. Now this is relative velocity. You can see here. Shall we think? This R1, VR1 is the relative velocity of the inlet one. VR2 is relative velocity of the outflow, inflow and outflow. Now, shall we think that the bucket moving speed is u, the bucket is moving to u, then we can derive that type of the velocity triangle. Then here is the angle of that the outflow, the angle of outflow is phi. Then the real one, absolute velocity, we can derive one, the VR1 cos phi minus u. This is the minus u part. Then this is the we required absolute velocity, outflow absolute velocity. So inflow absolute velocity is v1. The v1 we can write that. This relative velocity is here. Relative velocity is there. Now, then we can take these equations. I would explain that because of this absolute velocity is equal to the real one, as well as the outflow is this equation. The cos phi is coming. Actually, now you can understand very simple trigonometry. The VR2 cos phi is this angle. Then we need this part. That means this the minus u2. Then this is the VW2. If it is no friction, then VR1 and VR2 should be equal because of it like that. If it is coming in this side, coming in this point, it is smooth. That is smooth. That is smoothly passed to the velocity is here. Velocity at this point is equal. There are no friction, but there may be small friction. Then we can consider some small friction coefficient is there. Then we can define that the friction coefficient VR2 is equal K VR1. Now, it's a runner power. is we know the power into U in the first this Newtonian mechanics. We can use the power into U is a power. The power can be explained by the power force into U. Then there's a momentum theory we can use here to derive the force. Force mean apply force on top of the bucket. There's input momentum. This input momentum, mass flow, and the v velocity. Those are the output momentum. There's two parties there. Those are two parts. Shall we think is equally divided to these two parts, m dot 2 like that. Those are the absolute velocities there. Then this is the force. The force applied top of that bucket. We can derive that by using this velocity triangle, this simple velocity triangle. We know that the phi is a geometry. The phi is geometry. Now that BW2 and BW1 can be replaced by then BB1 and U. BB1 and U. Shall we think we know the U? Shall we think we know U and B1? B1 and U are the known parameters. Actually, this is B2 and V1 and this U also. No, the U2 and U1 and U all are equal because of the actually the U1. The U1 is the respect to this one. This all are equal. Then shall we think we can write this one. Now this is a force. This is a force. Then this power can be right by this equation. Then conversion efficiency. The conversion efficiency can be right that one. This is the input total power. This is the total energy content in the water. It's a kinetic energy. Because of the impulse turbine, we are using 100% kinetic energy. Actually, the Francis turbine is not all kinetic. Some the impulse that a kinetic and potential both can be absorbed by Francis wheel. However, the Pelton wheel is fully kinetic energy. Now, this input energy is output energy. This is conversion efficiency. This can be simplified by using this equation, this one. Then actually, those are the values are there. Then we can substitute these correlations to this equation. We can find out this conversion efficiency. This is the conversion efficiency of Pelton wheel. Now the cos phi and k. Cos phi and k should be also, we know this is k is the friction coefficient. Cos phi is the output bucket angle. Now we can find out for a maximum efficiency. We know the U, we don't know. U need to be defined. What should be the U should be there because of U is the speed of that bucket. Actually, the U is the bucket. That means RPM also we can find out because we know that R, the radius of that Pelton wheel is U is here. U is equal. That is U is equal R omega. Then if it is rotate at omega, that is R omega, especially the rotational speed of that Pelton wheel. The U is dependent on R omega. Now we know for optimization the derivation should be 0. There's a common mathematics. There's a common mathematics. Then there's a conversion efficiency. Then if we the U derive from U, then we can find out what should be the optimum U. Then optimum U should be half of that jet speed, the half of that jet, the water jet speed. Then we need to operate that Pelton wheel, that RPM should be, the rotational speed should be like in the similar way. That means if we know that V is, we know that's depend on that our previously V that head, if we know the head, the V is equal square root of 2 rho G like that way. Then the V is the constant. U need to be defined there. Now the K and phi also we know. If we use that, if we run the system, so optimum U, then there's a maximum efficiency. There's a maximum efficiency. You can see here now, it's a bucket angle also there, a very small bucket angle. Practically it need to be because of the zero bucket angle cannot be operated because of the same direction water cannot be returned because of not that's not practically. Then it need to be some angle is there. The K is a friction angle. If you think, you can see here the K is 1, the bucket angle is 0, there's 100% efficiency. The Pelleton wheel is 100% efficiency. If like that, but however, it cannot be. However, you can see the Pelleton, if the proper, there's a proper design of the Pelleton wheel, it can be very high efficient, which we are calling this a hydraulic efficiency. Then after that, hydraulic efficiency is converted to the mechanical power and everything, other losses also there. Then the turbine efficiency is much little bit less than that other losses also come in there. Then actually this technology, I would like to discuss the technology because of you can see here. Then actually nozzle, the nozzle, then we with a Pelleton wheel, we can use the many nozzles because of you can see here the Pelleton wheel, we are using only one bucket. At a one time, we are using one bucket. Then the other buckets are the idle. These are the buckets are idle. Then for utilize this bucket for the bucket size, the bucket, then we can use the many nozzles to utilize other buckets. Actually, we can the configuration can be like that. The many nozzles can be used. Then the bucket size can we make it optimum, somewhat smaller size. That's mean the cost-effective turbines. Then for a small scale, that a micro hydro level, also Pelleton wheels are commonly used people because of the high heat sites are there. Then 2 jets, 3 jets type of turbines we can observe. This is one site in Sri Lanka. Then there are many places people are using for a small scale wind turbine. The very small scale hydro turbines. Then there's a Pelleton. The Pelleton wheel is a very convenient one. Actually, in Sri Lankan situation, all the tea factories are operated by the Pelleton turbines in very old technology. It's a very common technology with good efficiency. Then it works like that. The flow rate can be operated by it's a nozzle controlling that flow rate can be controlled. Then it's depend on the required power. We can use the ply ball governors to control that RPM of these hydro turbines. Now, for a selection of turbines, is a rough guidance you can see here. The head and the volume, the Pelleton range. What are the Pelleton range? What are the Francis stain, the cross flow, like that. The large range can be covered by Francis wheel with the Francis turbine. The Pelleton is obviously like that. Also the head, even though 1,000 meters also can be handled by Pelleton with low flow, it's a low volume. The Francis is like that 500 megawatt, 100 megawatt, 10 megawatt, 1 megawatt also there. It's a cross flow is used for very small scale purposes, even though the reason is the cross flow is very simple as well as the conversion efficiency also not much high. These are the actually not only that hydraulic efficiency, the conversion efficiencies depend on the proper RPM and everything. We can find out these things. Okay, now actually some very small question session we can start with you. one question is I noticed that in the chat box. Actually, now you can ask any questions, no problem. Actually, I would like to discuss some energy storage also for a few slides before start that we can discuss something. This one question is there some hydro plants, some large hydro plant. Obviously, there are some kinetic energy in the downstream. I think that's the question is asked here. High kinetic energy in the water. We notice that high kinetic energy in the water. Why we consider? Yes. It asks that why we cannot use that downstream for a small hydro. Actually, I know that some places people try that type of concept, especially both and the one mini hydro, the one actually we are calling one small hydro plant was operated long time ago. Was operated in the downstream, and as well as there are some other configuration also there because of both and is a diverted one because of if it is working hydropower station, it cannot be released for the irrigation. If it is converted to the irrigation, then the water cannot go for a hydropower. Like that type of concept is there. Then in this play, then the one small hydro was operated in the both, and but I not noticed that any other places. Maybe some other maybe issues there is possible actually that possible. Maybe the some other implementation issues may be there. Where we can use that power, it can be used again to feed into the grid, the controlling issues, and then the technology can be used there. I can say can possible some places. Can possible some places. The one example is both and the previously was used. However, that power station was damaged due to that penstock failure long time ago. After that damage, that a micro hydro was plant was also not performed because of it's a flood. It's a totally flood at that time. So long time ago, actually, I also involved that project many years back. That's all my experience about this question. Do you need more clarification? Please ask that. Is it an answer for your question? Who asked that question, please?
Yes, sir. Okay, sir. Thank you.
Nalin, is that's the question you asked?
Yes, sir. I'm asking why we are not like Victoria, any kind of a major reservoirs. I have not identified there any kind of a mini hydro plant installed at the downstream. So that is my question. Yeah. Okay.
Yes, actually, I don't know exactly. Maybe there's a possibility. Actually, I know the only places both and reverse use, but now it's not operating. Then the mini hydro one, then would like to explain a little bit. There's an environmental impact and everything. We know the hydro, even though that the hydro is a renewable energy, the large hydro is damaged too much of that environment. So large hydro. Actually, now the world we cannot consider as environmental friendly because of it need to damage a lot of that impact blocked because I need to build a large reservoir, then divert rivers, then it affect to the flora and fauna and everything. Then, however, the damage may be the less if you are using small hydro. Somewhat small hydro, that damage is less. Then it can be also that also need to be considered. Then the hydro, actually large hydro, we are not considered as a those large hydro we are considered as a conventional power. So there's only small hydro are the renewable one. The people are categorized like that way. Actually, we are more considering in this lesson small hydro. Then actually small hydro is not required large reservoirs. Then it not much damage to the environment. The thing is that the cost of energy again need to be considered. If you go for a cost of energy again, we need to be considered. The piston type system. Yes, somebody asked the piston type system. The piston type system mean is reciprocating type one, no? Reciprocating type one. Why we are using reciprocating type piston type for a hydropower? Because of the, you can see here. Actually, I need to search that very carefully. However, we can see that if you go for a piston type one, the conversion efficiency is the comply with the Carnot cycle one. No? Generally, this is a Carnot, the concept of that that type of concept. Then generally, the conversion efficiency of the piston type, that's reciprocating type one, is less than 40. Obviously, that is less than 40. The conversion efficiency may be very much less compared to turbines. Turbines means the belt and wheel is much more efficient. But that is a site specific. Some places may be piston type that mean displacement type of the machines maybe can be operated, but I never seen this type of technology in the real practice. In the commercially, I never seen that. Maybe in the experimental, maybe in very much site-specific places, very small cases, yes. Piston type system has high efficiencies. This is very much controversial to me. Can you explain that why you're saying it is high efficiency?
So it is actually published in the television, I think news bulletin or something. I can't remember. Maybe
Yes,
about
the conversion, the piston type conversion efficiency is theoretically is less, not general.
Yeah, maybe that's why I'm asking whether it is accurate. So it is, I think, published on the news also.
Yes, actually, then we cannot say exactly because of which technology they are using. We need to consider that. But in practically, I didn't see this type of.
Okay,
maybe some invention like
Excuse me,
that.
Professor, for a reciprocating engine, isn't the expansion is very important?
Yes.
So how could water be expanded in a cylinder?
Yeah, that technology I don't know because of that. Maybe that piston type one I didn't see. Then maybe that pressure is used there. Maybe the pressure can be used to push the piston, like that type of concept may be there. Without knowing the exact technology, that mean exact the configuration, we cannot give any comment on top of that. If we have the exact configuration, we can see how it can be operated. Maybe the water pressure can be pushed the piston, then the valve can be divert to the piston by the like that. That can be maybe the concept there in the crankshaft. And if we have any configuration, we can check that how it's work. However, in the present scenario, in the commonly the people are not using the turbine is the most common concept of hydropower generation. Okay. Even though that you can see, even the water wheel, very oldest one, even the water wheel have the 50% efficiency, conversion efficiency. The very simple one. Then if you have the piston type one less than that one, why we are using that piston type one? Because of the water, even simple one, the water wheel is more than 50. There is 50% conversion efficiency. Okay, then I think this lesson is give the general concept of this conversion efficiency, the type of turbines, then actually the reservoirs and assessments. I hope we covered the last time up to some level. Then this technology conversion techniques we already discussed in this lesson. You should be able to describe the Peloton wheel, cross flow, the Bunky turbine, and Francis turbine. And those are the main the technology what we discuss in this time. What are the Francis wheel advantages as well as disadvantages? Then the which type of applications as well as what are the concept and how it's convert the hydro, the water power, the energy contained in the water converted to the mechanical energy. The controlling side, I'm not going to talk too much about that. However, then I spend a little bit for dummy loads and everything. But for a large hydro, if we're not using that type of on the vane, the guide vane, as well as the nozzle, can be control the water flow by respect to that water flow, can be control the power output the turbine, then can be controlled the RPM, that rotational speed of the turbine. Then shall we little bit discuss about the energy storage because of that energy storage also very much important section. Energy storage. Yeah. Why we require that the concept of energy storage, flywheels, ultracapacitors, pump hydro, compressed air storage, superconductors, as well as thermal storage, battery, as well as the hydrogen. Those are the main the practices people commonly in the commercially available technologies. Why we require that energy storage? We know that demand and resources are not compliant always. Definitely, what happened, especially in renewable energy, we cannot control the intermittent supply. Those are the main challenges what we have today because of if we go for we have many targets presently. We need to go for this much of renewable energy. We need to be absorbed. However, the main challenge is that the intermittency. The intermittency cannot be handled to use the useful energy to fulfill the demand. Then especially actually wind, solar like that. Hydro also the large hydro not an issue because of can be stored. How especially wind, solar, and these things there are a lot of curtailment in the world. There are many curtailment. So actually, one example I found resources. You can see here the presently some curtailment in some countries. You can see in the Scotland, you can see a 2.3 terawatt hours curtailment is there in the wind. It is much more that is comparatively larger than our world require because of that is intermittency of the wind power. That country cannot be absorb that energy because of that the grid and demand maybe not comply with that pattern. The pattern is not comply because the wind is available. There is no any demand there. When the demand is high, the wind is not available. Like that type of mismatch is here. Then it is very much important about the storage, that energy storage concept. And however, that energy storage is still challenging because of the tech. Even though technology is there, it is not cost effective. We cannot use that. Now, then this is the one. This is the one area you can see here. The thermal demand also there are some places. Then as well as this is the requirement of energy storage. You should be able to describe then the requirement of energy storage. Because of that requirement is coming because of the using of renewable energy is coming to the world. However, then there's one other concept of the thermal storage and everything. So optimization, the system optimization also we require the storage. Even though I can explain that, even though some vehicle also we are using storage. That means very good example is the hybrid vehicles like that. Because of this optimal operation of the plants, it may have some optimum capacity of generation. Maybe sometimes the coal power generation it required to operate optimum capacity. If it is derating, it under efficiency. Then what happens if it is run at optimum capacity? That power is not that power need to be stored in some places, right? Then especially in the that not only for biomass boilers, especially coal power course everything. They need to be operate optimum capacity to reduce the emissions and as well as conversion emissions. In this type of applications also, we require the storage. Then that is very good example of thermal storage. Now the people are thinking about the thermal storage, the cost effective compared to some other sources of that. Yes, explain that. Now, then this is the overall concept. Renewable energy is there. Then that can be used maybe hydrogen as well as storage of hydrogen. And the hydrogen is a very much useful fuel. So many research areas. The percentage the very big, the huge potential of the research in the present world. Hydrogen, usage of hydrogen, storage of hydrogen, as well as the hydrogen can be converted to many other fuel, maybe biofuel, maybe as some recovery of some other non-carbon fuel. We are using hydrogen. Then hydrogen is the main point here, not for direct combustion. It's maybe a fuel cell like that. Then energy or storage concept, battery, thermal energy, compressed air, flywheel, like that type of concept people are presently using. Then there's a mismatch of these things. Especially you can see here the wind and solar. Wind and solar. Sometimes coal power also, nuclear power also cannot be derated. And at that point, people need to be stored that power. Especially in the night time or some places, the coal power plant cannot be derated. Then that power can be stored some places. Maybe pump hydro. The pump hydro again is site specific. That's depending on the place to place. The potential may be different. Now, this is a pump hydro. The concept was almost same as hydro. Only thing is that the pump back to the reservoir. The pump back to the reservoir. The same turbine, sometimes same turbine can be used for the symmetrical type turbines. But however, it's better to use separate pumps because of it's much more efficient. Then if it is have the high high energy, the off-peak period, the off-peak power can be used to pump back. Yes, then it is again is at the point of required power, the turbine can be operated. It is simple concept. Conversion efficiencies depend on hydropower and the pump efficiency. Pump efficiency as well as the turbine efficiency we already discussed in our previous lesson. The flywheel concept also I would like to explain a little bit to you because of the it's very old concept. It's not new. The flywheels are using for many places. This rotating mass actually. Then I can go directly. Yes, this one. This flywheel is working like that. The flywheel is can be store energy as a mechanical energy. This moment of inertia is there. The flywheel is the large rotor. Then it's a frictionless one. Then actually, is a bearings can be very efficient bearing. We can use maybe the magnetic type bearings or sometimes floating bearings to make less friction, as well as it can be operated in the vacuum because of the frictionless. Then it's a frictionless. No any energy loss in that rotating mass. This is a motor and generator. The motor, if you need to store energy, then it's a motorized. That one is a rotate for high RPM. It can be store energy at the point of it required to release that one. This generator, the motor can be operated as a generator. It can be absorb energy. Then it's a very convenient and very old concept, as well as it's more reliable concept. Then with this concept, there is a theory is here. Actually, energy storage is half I omega square. This momentum of inertia is a very much important point. Energy storage is depend on this rotational speed as well as I. If you have the high I, the large I as well as a large omega, there's energy. That amount of energy storage can be we can calculate. This rotational speed and I. There are many applications. Some places the grid electricity also, the grid power also can be stored some places. Then as well as for the balancing, sometime for stabilizing the voltage. Then this type of flywheel is using, as well as the old days bus also, the one bus also operated. The bus can be operated because of bus is in the routing place. Can be used here. This is one example I found. Even though in the 1950s in Switzerland the bus was operated by flywheel. The flywheel, because of the bus at the bus stop, there's a power supply is there. Flywheel can be charged by the power supply by motor. It can be run till next bus stop by using flywheel, because of there are not required any hang off power lines and everything. It can be because of bus is the planned route is there. Then by the bus can be operated like that. Then one example I'm going to explain that how much of energy required to operate that bus. What's the difference of that each bus stop? We can design very clearly the size of the flywheel and the bus stop, the distance between bus stop. Now, presently the flywheels are operating to improve the fuel efficiency of the buses. The same as a hybrid vehicle. The concept is almost same as a hybrid vehicle, because we know the combustion engine is this optimum, the maximum efficiency if it is run at a certain optimum rotational speed. Then it need to be operate the certain capacity. Its optimum operational condition should be there. However, in the vehicles, we cannot run that optimum conditions if we use directly engine. Then if we use engine for a vehicle, we cannot maintain that optimal level of the engine. But if the engine is coupled with any energy storage system, the engine can be operate at the optimum condition. If it is excess energy, can be stored at that energy storage. If it is if you require more energy, then that energy can be drained from that energy storage. The flywheel can be used here without instead of battery, the flywheels are using here. Because of the buses, no problem. The flywheel can be installed inside the buses. Then that is a very good option. Then so flywheel concept also there, as well as the flywheel also using for energy storage for large system also for some. Now, the superconductors also. Yeah. Then as well as you can see that some comparison of these various energy technologies, the flywheel, batteries, compressed air, pump storage, hydrogen, and the methane and other things. Then you can see here the capacity, storage capacity, and discharge time. Then each and every technologies we can consider, we can select with our applications. Then you can see the flywheel are not cannot be used for a very large applications. However, till 100 kilowatt hours we can use there. The batteries also very much useful. Then you can see here batteries also people are presently using. This is also some 2015. Maybe some technologies are improving for that is especially for batteries. People are much consider for battery improving now. Still, the battery capacity also like that. Compressed air storage, pump storage, and the hydrogen power to the gas like that. Then those are the compressed. However, the cost of energy is not considered here. If you think about the cost of energy, again we need to be considered how much of the cost of energy storage also need to be considered. I'm not going to discuss too much about batteries because of it is commonly that technology is commonly available. You can see here the comparison of this technology is a battery. Each and every battery is also the rated power as well as the discharge type. This selection of batteries also there. Now you can see here the comparison between the battery and flywheel. Battery and flywheel, obviously, it's depend on the application. We need to think about that. Now, ultrasonic shall we go for a compressed air? Compressed air storage also. We have to think about that. It's commonly used for many places. We know that the compressed air, because of the compressed air can be normal air can be compressed and stored in underground cavities. That's a general way. If in places we have the underground cavities, we can store there. Otherwise, we can use some storage tank, obviously. Then, if you have the off-peak time, is a compressed air is stored at that place. Then the peak time, the compressed air turbine can be operated, and that generate power. There is a basic concept here. However, we know then when we compress the normal air, that has some other phenomena can be happening. No, so what are the things? This compressed air has basically 3 types. We are calling adiabatic storage system as well as the diabatic storage system and adiabatic, and other one is isothermal. So basically 3 types of there. When we compress these things, it generates heat. It releases some heat. Then as well as if it is need to be used for a turbine, it absorbs some heat because of expansion and the compression. That mean at the point of expansion, it required some heat. Then there's a main challenge to overcome there. Then if you the diabetic storage, the diabetic things, we are not consider about that. When we compress one, heat is dissipated. Heat is dissipated. Then at the point of turbine working, we need to supply some heat there. Heat need to be supplied because of otherwise because of heat. There's a heat requirement is here. There's some heat requirement is here. Then it's an adiabatic one, the compress one. It's a highly insulated. Here is a highly insulated. This one that is stored at high temperature. That store at high temperature, somewhat high temperature. Then that at high temperature compressor can be used as it is for a turbine. As it is for a turbine. Then this isothermal one. There's a most possible technology. The separate heat thermal storage system we can use here. Then what are the mean that at the point of compression, that amount of thermal energy is stored some places. At the point of expansion, that the same energy can be used. That is utilized at that point. Then these are the 4 technologies for a compressor. Thermal. These are the basic 3 technologies we can use as a compressor, energy storage mechanism. Then now this is a technology what I need to explain with you. This this thermal storage system also there. This ambient air, this is a compression, off-peak time, it's energy, the motor. This work as a motor. That's work. There's a work as a motor, compressor. Then this storage system. At the point of storage, it releases heat. There's a heat thermal storage system also there. Thermal storage in some liquid or the material can be used, as well as the phase change also used. Generally, the phase change is commonly used because of the CP. That means latent heat is the highest thermal capacity point. Then the high CP material can be used here. There are many liquids are there for a high CP one. Then the salt and many things. Then you can find out what are the suitable the material for thermal storage systems. Those are the insulated chamber. Then it can be stored thermal energy. Then there's a compressor. It's a low temperature because of high amount of air can be stored here. Then at the point of it released for a turbine, then heat can be added to the point because of it requires some heat to expansion. Then this work as a generator. Then in the similar way, this is the main concept of thermal. This is the main concept of compressor storage technology. Now, actually, compressed air vehicles also now common now in the market. People are using that compressed air vehicles, but a small amount of the fuel is using for a heat source. Very small amount of because of combustion is required to heat that at the point of expansion. Now, this is the how it's working. Thermal storage also. Thermal storage is very commonly used for a solar system, especially for concentrated solar. We know the concentrated solar is generated at a high temperature because there is concentrated point here. Then that the solar energy is highly intermittent because of only daytime, only 6 hours time can be harness solar energy. Then that energy can be stored as a thermal energy. Then there's a thermal energy system is commonly used for solar power, concentrated solar. Then you can see here for turbine. The turbine can be operated continuously throughout the day. Then with that storage system, then is properly designed thermal storage with the properly the capacity of the concentrated solar. Then this turbine can be operated throughout the day with the fulfill of the demand. Now you can see here in the present day, also Sri Lankan situation, our solar now the solar is challenging without storage. Now this technology is very much useful. Now you can see here that the concentrated solar conversion also little bit high compared to solar PV, obviously. However, this overall efficiency, the turbine efficiency, obviously much more high. The turbine can be operated more than there's overall efficiency is more than 60-70%. With the thermal storage, is a good conversion efficiency can be achieved in the system with the concentrated solar. This concentrated solar also all energy can be absorbed. So all energy can be absorbed. Almost all energy can be converted to thermal energy. Some losses are there. There's a reflectivity emissions and that is comparatively with high conversion efficiency compared to the solar PV. However, the energy again I can explain it again. The cost of energy need to be considered. I'm not going to discuss too much about the concept. The concept of thermal storage system, then the materials and everything. And if you go for that Learnify lessons, the one that been recently, we could publish some paper regarding that thermal storage systems, the material selections, and all literature. If you read that paper, you can have a good idea about that the material selections and the concept of thermal storage technologies. Okay, now those are the main concept what I need to discuss with you regarding energy storage. Today we discussed a little bit deeply the flywheel and compressor. The battery technology I have not discussed too much because of the large area. Hydrogen also I have not discuss. The hydrogen. Oh, okay, we can little discuss about hydrogen. Hydrogen can be generated generally by renewable energy. Many technologies are there. If we have the excess electricity, we can use simple electrolytes to convert that electricity to hydrogen. Hydrogen storage and everything is very complex. That requires special containers and its transportation and everything. Then there's one mechanism to generate hydrogen. Other one, if we have that biomass, one of the pyrolysis, in the process of pyrolysis also, we can generate hydrogen. In the controlled pyrolyzing process, we can generate hydrogen. Then as well as we can use the methane, the biogas. For biogas, also people are using to generate hydrogen, the methane, by using that the process. The biological process also, the controlled biological conversion, so some bacteria, and the control process of the biochemical processes, we can generate more hydrogen. The hydrogen degeneration concepts are there. Then in the process of the petroleum industry, in the petrochemical, also hydrogen as a product, as a byproduct. Many areas, hydrogen is very much interesting area present days. The hydrogen, people are saying it's a future fuel like that. Then that also the energy storage mechanism, because of hydrogen can be stored up to some level. That hydrogen can be used to recover some other material, some other fuel sometimes, because of the regeneration purposes sometimes. So the hydrogen useful material. Hydrogen can be converted to the fuel again, the biofuel. Then if you have the hydrogen, it can be converted to the methane, be very easily stored someplace. Like that type of concept is there. Then there are a large amount of researches going on per days. Okay, if you have any questions regarding energy, or you have any idea about that, because of renewable energy is coming with the energy storage, because of without the intermittency cannot be handled. That's the biggest challenge. You can see here, the curtailment of some countries is very much huge. They also facing that 2 terawatt-hours, many curtailments. That is especially in the wind energy. This is a very small homework for you. And again, you can check that. You can see, shall we think, some passenger bus drive with the flywheel. There's a flywheel, the mass is 1000 kg. The diameter of that flywheel is 180 centimeter. It can run up to 3000 revolution per minute. The RPM is 3000. Then you generally calculate at a top speed. That means top speed means 3000 RPM. How much of energy can be stored? What the kinetic energy of the flywheel? How much of energy is contained there? These all equations are given here. Then the moment of inertia for a drum, the solid drum is calculated by the following equations. I is equal to mr square divided by 2. Then it's 1,000, that's 3,000 RPM. The 0 to 3,000. It's 0 to 3,000, how much of energy can be stored? Then as well as the bus consume 20 kilowatt for a constant driving pattern. What should be the time in between two stops? Actually, speed is not given there. It is that means the bus speed is can decide maybe the constant speed. How much of time stop? The time between two stop, and then you can calculate. Please consider this as a homework. There's one application. There's a very nice application. It is renewable energy. How we can use renewable energy for transport? Because of the if your grid or that charging point is operated by renewable energy, very cheap energy. Use a converter to the transport is very complex. If you use a battery also not for a large vehicle, feasibility is little bit controversial still for buses like that. How the flywheel, the concept of flywheel can be used here. This flywheel effect is using for a wind turbines also for a smooth wind power sometimes. This depends many places. Flywheel effect is separately using here. Okay, I think if we have not any questions, we can wind up the session today. Okay, thank you very much.
Thank you very much, sir.
Thank
Good
you,
night,
sir.
sir.
Good night, sir.
Thank you, sir.